Today, I'll be talking about some recent work that we did on relaxed labelship. This was joint work with some collaborators at Amazon, and I really thank them for the compute because this project needed a lot of compute, and definitely for all the mentoring and advising. Okay, so we've seen sort of huge success of machine learning in standard supervised IID settings, ranging from like ImageNet applications to like performing good on like some tasks. Like AlphaGo and things like that, which has inspired applications in medical domains. And sort of over like last 4-5 years, we have seen a lot of superhuman performance in IID settings in like problems in like dermatology and retinopathy, diabetic retinopathy. However, this success is sort of usually restricted to IID settings, and it is well now understood that okay, standard machine learning at least breaks under like distribution shifts, and there have been like many articles that sort of try to highlight pitfall on how sort of these machine learning models fail under distribution shift. And there was one paper that showed that for COVID-19 chest radiographs, most of the machine learning models were getting below performance of like a baseline or like even a random baseline. And there have been many surveys that have sort of shown that either due to spurious correlations or due to some underlying biases or like methodological flaws, things that may generalize IID does not often generalize OD. So and one sort of and the progress in the community has sort of focused on benchmark driven empirical research. However, in this talk, I'll try to sort of highlight in one specific problem that there has been some lack of rigorousness in that benchmark driven progress, and we'll sort of highlight some issues and try to fix them empirically. So distribution shift in some sense can happen in multiple different scenarios. It can, so here I've listed sort of three, which are not definitely like exhaustive or covers the full subset, but there are sort of three commonly studied scenarios. So one is domain generalization scenario, where we observe label data from multiple different domains, multiple different source domains. And the hope is to generalize to a different unseen test domain that may share some similar characteristics of training domains. And then there's something called transfer learning, where we have some amount of like small amount of labeled target data, that is data from which we are getting sort of our test examples, and we are allowed to sort of overfit or like fine tune on those. And then the third is this domain adaptation setting, where we have labeled source data where we can train a model. And from the target data, like the target domain of interest, we may have unlabeled data. And we are sort of allowed to adapt to that unlabeled data to improve sort of on that target domain. And at a high level, these settings sort of differ in what data is available during training. In this work, we'll focus on sort of domain adaptation problems. So yeah, let me introduce the setup a bit formally. So here we assume that we have data from source distribution, some n examples from source distribution, and the distribution may shift to some target distribution PT, from which we only observe unlabeled examples. And at a very high level, the goal here is to predict well on test distribution, that is this target distribution. So I'll use test and target a bit interchangeably without seeing any labels from target. And please feel free to interrupt me if there's any clarification questions, even on Zoom. So yeah, I think I might not be monitoring chat, but please feel free to just unmute and speak out your question. Okay. And in this talk, in particular, I'll sort of focus on distribution shift problems that arise due to changing class prevalences. And I'll make it clear what do I mean by that. So consider this archetype example, which is in like medical domain for like disease diagnosis. So let's say we have labeled data from hospital 1 on some respiratory classification problem where we have diseases like pneumonia, tuberculosis, and asthma. And let's say these were the prevalences of these different diseases on the training data from hospital 1. Now, let's say you train a model in hospital 1 and deploy it in another locality. What might as well happen is due to changes in locality or like changes in like over the time period, the prevalences of different diseases can change. And then this brings in sort of an IID violation in the sense that now because these prevalences are different, now your data from hospital 2 is no longer IID to hospital 1. So can we rely on the model that we are deployed on, like, let's say hospital 1 to do very well on like hospital 2? And are there like scopes of improvement when we may have some information about how, when we have this unlabeled information from hospital 2? So let me present like first a formal instantiation and a simplified setting where this may happen. So assume that our label proportions py can change, but the class conditional p of x given y doesn't change. So this is the standard classical label shift setting, where in this setting we sort of obtain a well-posed setting. One thing that I want to make clear here is, in general, these domain adaptation problems are underspecified in the sense that there can be multiple different solutions that all do very well on source, but can have in general different accuracies or like different performance on target when we only have access to unlabeled data from target. However, when we impose these assumptions, we get a well-posed setting in the sense that under some additional benign assumptions on how p of x given y is some sense a span of your input space, you get like a well-posed setting. That is, there will be sort of a unique solution that will perform on target.
Quick question.
Yes.
Does the p of y change here assume that the support remains the same, as in like?
Yes. So
okay.
we'll come to that. So yeah, so here, at least for now, let's assume that you're not seeing previously unseen labels. But yeah, I'll touch that point like soon in like next few slides. Yeah.
Or the other case of also like having previously seen labels being dropped, being set
that
to
can happen.
zero probability.
Yeah, that can happen. The thing is, we should like in some sense, we are not allowed to see previously unseen classes, but previously seen classes can get dropped. That's okay. Does that answer your question, Lucio?
Yes. Yeah. Thanks.
Okay. So here we can sort of the high level goal of performing well on target can be sort of divided into two tasks. One is estimating the target label marginal, PT of y. And second, maybe by leveraging this estimate, we want to adapt a classifier that we have trained on source to target data. And just to make sure that we are all on same page, why this task is non-trivial, recall that we do not observe target labels. So we cannot in some sense just do some counting and get some estimates on target data. So under label shift, effective methods exist, methods that leverage sort of black box classifiers to get estimates of target label marginal, which has in some sense some form of like minimax optimal guarantees with 1 over square root n convergence rates. So those things exist when we have the assumption that p of x given y doesn't change. And by leveraging these assumptions, by leveraging sort of this estimate of target label marginal, we can also do a post-hoc correction or like an on-the-fly update of source classifier that performs an important importance reweighted softmax correction. Okay. So this is something that has been done in the past and is sort of widely studied. But now we want to sort of extend this label shift setting to sort of tackle more scenarios that may appear in the wild. So two key assumptions that we make in this label shift setting is one, we have this class overlap between source and target. And the other is we assume that p of x given y remains invariant. However, as I mentioned, like these assumptions can be violated in practice. We have some past work on PU learning and open set label shift that relaxes sort of the class overlap assumption. So that is there, like we can in some sense allow for previously unseen classes, and under some more additional constraints between sort of between p of x given y from the new class, we can also make sure that those problems are sort of well posed and there are sort of solutions under those settings. In this work, we aim to sort of relax the second assumption, that is, we want to allow changes in p of x given y. So that will be sort of the high level, like this will be the sort of high level setting that we'll be discussing in this talk today. If there is any question at this point, maybe I'll pause for a minute or like for 10 seconds. Otherwise, I'll continue. Yes.
So I know you were talking about a setting where you don't have any labels for the target.
Yes.
What would happen if you did? Would you do something completely different?
Yes, so that would sort of fall in the second category of techniques that we had, which is like if you have small amount of target label data, then you think about some fine-tuning procedures like, okay, maybe you want to train, let's say just the last, like do some form of linear probing or update just the batch norm parameters or things like that. Like people have tried a lot of things. And there's also like a huge literature that is emerging in like these pre-training, like large scale pre-trained models, where you want to sort of continually adapt even with like label data. But yeah, that would be sort of different. Yeah. Okay. So what is the motivation of why we want to sort of relax and allow for shifts in p of x given y? So let's imagine that when the data sort of shifts from, like when the distribution sort of shifts from hospital 1 to hospital 2, along with changes in class prevalences, if I were to plot a per pixel intensity plot, like a histogram plot for each of the classes, averaged uniformly, then we do see that for different sort of hospitals, due to differences in like the techniques that they use for radiography, imagery, and things like that, the histogram plots differ a lot. So this in some sense shows that P of, and this is real world data. So we have sort of taken this from some past work where people do observe that the label proportions change a lot. And simultaneously, there are some shifts in P of X given Y for each class. Okay, so this sort of motivates like the relaxed label shift setting. And just to make the setting sort of very clear, here we assume that P of Y can arbitrarily shift. And for now, we'll say that P of X given Y can shift in seemingly natural ways. So what do I mean by that? I mean that these kinds of shifts are sort of motivated by things that appear in practice. So for example, let's take the chameleon corpus. There we have data from hospital 1. And in hospital 2, the way in which these images look in terms of their intensities are slightly different because of different pigmentation techniques or like different tools that they use to finally get to these images. And there can be like different types of naturally seeming shifts. One such is like in Living 17, where the distribution of P of X given Y shifts to have different subpopulations. That is, the populations of, for example, let's say apes may have like class A and B, whereas in test, you may have class C and D. And similarly, like for CFAR 10, here we have changed in some sense the saturation of these images. and these things can also happen in like tabular or like NLP datasets. So basically, we'll assume that this P of X given Y varies between source and target in some comparatively restrictive way. And a mathematical model, if you want to think about this mathematically, we can think about that there is some divergence constraint on how much P of X given Y can shift. Although for the purpose of this talk, I'll, except for like one result towards the end, will not be discussing any instantiations of D, but instead focus on datasets that appear in real world and the shifts that sort of we have seen in some of the benchmarks that are taken from like these practical datasets. And the reason is because there is some sort of like lack in rigorous characterization of how those shifts actually appear in practice. And the goal here would be the same as like the label shift setting. That is, we want to estimate target label marginal, and at the same time also adapt the classifier F that we have trained on source to target data. Okay, now people have looked at a lot of like different domain adaptation problems, but one common problem that we encounter in most of these academic benchmarks is that they exhibit sort of little to no shifts in label distribution because these datasets are sort of carefully curated. In most of these datasets, the label proportions in source and target are either being like sort of explicitly enforced to be the same because of cleaning procedures that they might use, or so that is something that we have sort of observed. And I've shown here one instance of such dataset, which is FMOW wilds, where we can see that the label proportion shift is actually very minimal. But in practice, when we only have unlabeled data, we may not always be able to sort of enforce this. That is, the label proportions in your unlabeled data can be very different from label proportions in your source data. And as a result of these benchmarks, what we actually observe and will show in a few slides, that these benchmark-driven research have produced heuristics that implicitly assume that there is no shift in class balance. That is, if now the class balance would shift from source to target, these methods falter, and they falter terribly often. So we'll show in some slides that these methods sort of even do worse than doing no adaptation. And I'll get to that. Okay, there's also like this another line of work where people have tried to tackle these relaxed label shift problems, but this literature is sort of emerging very recently, and it is very difficult to sort of assess the state of the field right now because evaluation criteria in different papers are different. They evaluate on like completely disjoint set of data sets. There are missing simple baselines, which they should include. And we show that some of those simple baselines do much better than all the methods that have been previously proposed in these recent papers. And also there are some issues with model selection criteria because fundamentally we are only looking at like unlabeled target data. So in practice, we should not do any model selection by peaking a target validation performance. However, previous papers have been a bit unclear about how they actually ended up selecting their final models. So in our work, we sort of take specific care to make sure that we lay out all of these things on sort of a common ground and then make these comparisons in sort of a fair and like realistic way. And while by doing that comparison, we observe sort of these things that, okay, there have been some issues with like prior methods implicitly assuming that the label proportions don't change. And also at the same time, we can do much better than these methods by very simple baselines. And we'll see that soon. But yeah, if there's any question here, maybe I'll pause again for 10 seconds. Okay. Okay, so now maybe I'll quickly introduce the benchmark that we have and sort of move on to presenting results on that. So we created a benchmark where we take 14 different multi-domain datasets. So by multi-domain datasets, we have datasets where we have different shifts in P of X given Y, on top of which we simulate label proportion shifts of different severity. And by doing that, we get sort of approximately 500 different distribution shift pairs among source and target. We train 12 popular domain adaptation methods, which include methods in like domain invariant representation learning, self-training, and test time adaptation. And so basically the results that I'll sort of present next are findings from doing this large scale sort of study. And just sort of showing so these are sort of the data sets that we evaluate in our, that we sort of leverage in our work. So these are all existing benchmarks where on top of these shifts in P of X given Y that are there in these, we simulate label proportion shifts. And just to show like a subset of what these data sets are, I have a slide here which shows that on FMOW, the shift is happening over years, over sort of like different years over which they've collected the data. For Chameleon, it's again the hospital, like different hospitals in test and train. For NTD13, they are like different subpopulation shifts or like shifts due to these replication studies that are also like appearing due to how, due to human preferences and things like that. Okay. And as I mentioned before, we simulate because these data sets do not show any default shifts in label proportion. We simulate shift by altering target label marginal, keeping the source fixed. And how do we do that specifically? We sample different label proportions from a Dirichlet prior, where we vary the prior parameter alpha. That is, in some sense, lower the alpha, the more severe is the shift. And by doing that, we obtain like some sort of pairs in source and target. And this slide sort of shows how our sort of simulation, how we actually simulate shifts. So we have these different shifts in P of X given Y. And for each shift in P of X given Y, we have different proportions of label shift. Yes. Yes. Yeah. Yeah. Yes, by assuming that, yeah, like real world process may be like more closer to, let's say, sampling from like a Dirichlet prior. And I don't have results right now in the slides, but we have validated these findings on real world data sets where this label shift label proportion shift happens due to nature. So we have like some results in some data sets on wild time, which is like a recent repository. So I have not included those in slides, where we see that we don't need to always simulate these label shifts. There are more recent benchmark, like benchmark that was released in Europe, where this happens by default. So there we also see the behaviors that we see with like simulating label proportion shift. Yes. So the difference here is we are now, so basically here in the blue, we see the source label proportion. The difference is in most of these data sets, the source label proportion and target label proportion is the same. So this is what the original data sets had. And what we are basically saying is the label proportions now can be different. Even though this is simulated right now, what we are sort of going towards is like a more rigorous and more exhaustive evaluation where these proportions can change. And the sort of remark that I made is, we don't need to do this. Like, after we release this study, there is more recent benchmarks where datasets have this property that label proportion shift and findings sort of transfer. Yeah. And yeah, like this is again like a slide of, for people who are interested, like these are the methods that we evaluate. I'm not going to discuss any of these methods in particular, but at a high level, what these methods try to do is, so there's this source only model training, which basically trains only on your source label data. Methods in domain alignment, self-training, or like test time training methods, they try to like use your unlabeled data during training your model, and try to either do some form of pseudo labeling or support matching while trying, like support matching objectives while trying to train. Yeah, and one more thing that I want to clarify is, like, we have sort of made few things very clear in the benchmark, which is, okay, we want to focus on how we select models in our evaluation. So we only use source holdout performance for selecting models. For DA method specific hyperparameters, we sort of fix those parameters across all different datasets. So we have not changed DA method specific parameters across different datasets, because it's almost impossible to tune them if we don't have labeled data from target. And there are more details about what architectures and pre-training techniques and data augmentations we use. But okay, so the first takeaway that I sort of trying to highlight here is basically the faltering of like these deep domain adaptation heuristics. So here, to explain the plot on the x-axis, as we go from none, 10, 3, 1, and 0.5, the label proportion shift severity is increasing. So source, we can imagine, is close to uniform, and your target label proportion is becoming a little more, let's say, peaky or like heavy tailed. And what we see here is that relative to source only performance, with which we have centered the plot. So here, line at 0 is source only performance. So what do we see? We see that as the severity of label proportion shift increases in my target, three methods that I show here, and I'll show more in the next slide, they tend to falter, and they falter in the sense that they start performing often worse than a source only model. And we show that this failure is not restricted to only those three methods. It happens for almost all these other methods, which are.
Why? So for minor shifts, why would you expect it ever to be better? You're saying that as the x-axis gets further to the right, it's getting worse.
Yes.
Yeah.
Yes.
But like even when it's anything greater than none.
Yes.
Don't you expect it to be worse?
When do you expect it to be?
Like what? Maybe I'm reading the plot, but like that black line on the left.
Yes.
That's just training on the source data.
Yes. So
should you expect to be worse on your target data?
So the thing is, we have centered with respect to target performance. So this, so basically this 0, you should imagine as performance of a source only model on that target. Yes. Okay. Thanks for that question. Yeah, I think yeah, I should probably clarify that.
That makes sense.
Okay. So here basically 0 is the performance of source only model on target.
Okay, so but when there's no shift, when
Yes.
When it's on none, when it's infinity, is that basically saying the target is the source?
No. So the thing is, there are some natural shifts in P of x given y. And what we are basically showing from this plot is that we have made some progress in capturing these natural shifts, in the sense that we are now like there's some heuristics that are often improved when there is no label proportion. So this is exactly what the none column would highlight here.
And the where the blue dot is that the mean?
Yes. So yeah. So the plot. Yeah. So this in some sense, because this is over like 300 different distribution shifts, I didn't want to capture variance, because variance here is not giving us the right metric. What I tried to plot is, so this is a box plot of all the differences, and the blue and the dotted curve is basically the mean of that. And we can see that even when the mean shifts, you can see the boxes, like the box plots together, sort of go down. So it is just to show that the trend is going down, but there are definitely many outliers where things don't hurt, and that often can change mean in some of these data sets. But yeah.
Quick question: are there any situations where we'd expect this not to happen? Like, it seems I don't know, maybe like this is my naivety speaking, but it seems as if it's obvious that the more severe the shift is, these methods shouldn't work in the first place. I'd rather be surprised if they did work.
No, so I think the thing is on tabular. So these are the results on vision modality. In tabular modality, I actually observed that it goes worse. But so here, in some sense, we should imagine that there is some trade-off that is happening from the benefit that we get by adapting for P of X given Y, and worsening of performance that happens due to shifts in label proportion. So in some sense, okay, if there is like the benefit that is coming from adapting from P of X given Y is more than the hurt that you have, which is incurring due to like shifts in P of Y, we may see that these adaptation methods still helping. So for example, for Dirichlet shifts at 3.0, we still see that overall there is some help. And that is because of this trade-off I just mentioned.
So to basically to paraphrase, it's like the issue is basically that there's two types of shifts happening, and these methods basically model just one type of the
Exactly.
shift, and
Yeah,
that's what.
yeah,
Okay.
yeah.
Okay.
You're correct for one type of shift. Yeah.
Okay.
I guess there was one more thing you should have calibrate both together.
Yes. We'll get to those soon. Yeah, so in some sense, IWSedan, and Sentry aimed to solve this problem, but we see that when we have like this fair evaluation, we don't really see those methods actually helping. So there are methods here in this span of like 12 different methods. There are some methods that were specifically proposed to also tackle the problem of like shifting proportions, but they actually end up not helping that much, except on few data sets. So one more thing that I should mention is we've done this study on like many more data sets than previously explored in these methods. I think there was one.
I was just curious because you got a tangent. This shift considers all the labels kind of, I would say, equally.
Yes.
But is there some sort of like maybe like an average or that type of situation where we weigh the labels and then shift the data? And we know that the model means one part of label where.
Yes.
And in this coincidental way, the weight to that label was more.
Yeah.
So your accuracy would increase in such a situation.
That happens. So we'll see soon that often, in some sense, when we are going towards the right, the problem can sometimes become easier because you were good at a label and that label proportion was very endowed.
How to differentiate between my model actually doing too well versus this shift which I did was convenient for the model.
So yeah, I guess the hope here is that because we have simulated so many shifts, on an average, we expect to see the behaviors that may arise. Like that's basically, we are expecting that it'll not always be the case that we'll randomly choose a class on which model was sort of better. But that's why I'm saying like we have evaluated these on like real world data sets where these sort of things continue to happen. Yeah. Lucy,
Sorry, I have another question.
Yeah.
Oh yeah. So this is assuming that you have no access to any target label data.
Yes. Yes.
Oh, okay. If you did, then what would make sense would be to do some sort of modeling the joints instead of making an assumption on P of X given Y and P of Y.
Exactly. I think that's
Okay.
what even I think Amit was asking, and yeah, I think that would then bring us to like a different, yeah. Then we'll have to also like change the comparisons that we do. But yeah, here we are assuming that we have no access to target labels.
All right. Thank you.
Yes. Okay. So here we have highlighted that okay, these methods sort of can falter when there is shifts in P of Y. And this, we are not like the first ones to highlight this thing. There has been some work in highlighting specifically for like these domain alignment methods that this failure exists. We in this work show that this is not just for domain alignment methods, but beyond it, like for methods like self-training. And it's still unclear why this happens with like these methods of like self-training when you're trying to like overfit to a pseudo labels, that you would in some sense degrade your performance when label proportions shift. And this is something that we are still exploring. Okay, so now we include some simple baseline corrections, and we want to see how those baseline corrections might help with this relaxed label shift problem. So here I'll introduce sort of two general purpose corrections that we can sort of plug in with any domain adaptation method of choice. So the first is resampling, where we basically try to pseudo balance the target data and source data to have the same label proportion. So what do? We label our unlabeled target with the classifier at iterate t. We get some pseudo labels y hat. Then we do some form of class balance sampling. That is by imagining that y hat t were the true labels. We would sample as if we are sampling from, let's say, uniform label prior. And we would resample this data set, perform one iteration of your choice of domain adaptation algorithm, get the new classifier, and repeat this procedure. So in some sense, this DA algorithm can be any black box method. What we are trying to do is we are artificially trying to balance the unlabeled target data and source data to a same label proportion. Now, there can be different choices of what label proportion we use. In this work, we make them to like uniform label to uniform label distribution. So basically, we actually balance out the class proportions to have uniform class balances. So that is basically trying to have this resample data. That is basically this resample data should have close to like uniform label prior on either the pseudo labels or true labels in case of target and source data set respectively.
Question.
Yes.
Yeah, it seems as if, so if I'm understanding what this algorithm is doing, it seems as if it's basically trying to assume like maybe the best thing we can do is to basically assume a uniform balance over the different classes.
Yeah.
But then if I'm to take a naive analogy, it means basically that you are basically have like in terms of like the Dirichlet process, you basically have this centered, what do you call it, balancing, but then you might end up, because you're centering, basically do really badly if you are, there's no shift in the source distribution or there's like an extreme shift. So it's like you're basically assuming that like being in the middle is the best thing to do.
Exactly, something like that. Yeah.
Okay.
Yes. Yes. Yes.
They're not accurate.
They're not.
So, but you know, we can make our algorithm more conservative. I think they can put stress to their confidence and like certain people and some of blah blah blah.
That's a great point. So that will automatically happen on how these DA algorithms then use your resample data point. So for example, fixed match does exactly what you said. So fixed match takes in your inputs and only overfits to those pseudo labels that have confidence greater than some fixed predefined threshold. So that will automatically be handled by, like in some sense, your DA algorithm. What we are trying to just say here, and this is a baseline correction. We want to see that how this baseline correction performs. We can improve on top of this baseline correction by restricting on how we would rebalance the data set. But this is like one correction to sort of start with.
Okay. So,
yes.
So basically, so I would imagine that if this uncertainty is correctly calibrated, then essentially you have your source data, put your target, you are really not confident about anything.
But that doesn't happen. That's what we are trying to show. That even in fixed match, we see that the method sort of goes terrible when there are extreme shifts in
because if the model is made with uncertainty.
Yeah. Like I don't know the underlying reasons why exactly these methods fail, but I have like speculations which are like it is trying to sort of overfit to label proportion, and in some sense because the initial model was trained on sort of some different label proportions, it ends up actually overfitting, and the final, let's say, pseudo labels that I get are very different from the actual pseudo labels. Like if I plot a distribution of pseudo labels that fixed match has at like, let's say, label shift 0.5 is very different from the proportion of actual like true labels. So in some sense, it's getting the label proportion incorrectly.
So they're wrong. But we can, what I'm trying to say is that we can look into what happens in this algorithm just by scoring those labels and saying, "Look, guys, I get this type of accuracy in my pseudo labels. You know, they're 70% correct or 90% correct, and I put this threshold, and as I put my, let's say, conservative threshold with lambda that you mentioned, I get less pseudo labels, but more accurate and so on."
But eventually what happens, even if we do those techniques, eventually it will end up pushing all the examples to a very high confidence. And there is sort of, even in this implicit curriculum, almost all the target unlabeled points, because they are fixed, you'll end up getting overconfident predictions eventually. And those uncertainty based on, let's say, the max confidence doesn't actually help us that much. Like that is exactly the kind of failure that we're trying to show. And we'll see that how this failure sort of simply fixes it. I definitely agree that there can be improvements on top of this, but this is one baseline correction that we have. Okay, this resampling correction, basically, this resampling correction tries to train our classifier F on mixture of sort of balanced source and pseudo-balance target datasets in an ideal case. But this still leaves open the problem of adapting F to original target distribution, which is still not available. That is, F is like this classifier F is still not calibrated to your original target label proportions. We have trained F on some pseudo-balance target distribution. And then we have this reweighting correction, which estimates target label marginal with existing label shift estimation techniques. For example, BBSE and MLLS, I can describe them towards the end. At a high level, these methods take a black box classifier, unlabeled data from target and labeled data from source, and spit out an estimate of target label proportion. So this PT hat Y is basically an estimate of target label proportions using some of these label shift estimation techniques. And we can use these estimates to reweight the softmax prediction. That is, we can perform a post-hoc correction where we change the softmax output of class J by multiplying with importance weights. The importance weights are obtained by these label proportion estimates. If there's anything unclear in this second step, so we call this as like reweighting, but this ideal like post-hoc reweighting of your softmax predictions. Okay. And yeah, the high level goal is, okay, relaxed label shift problems do violate the conditions that are required for consistency of these label shift estimation methods. We want to see how these methods empirically perform and do these techniques actually end up helping. And what we see is when we employ these techniques one by one and together, we see that in some sense we can empirically avoid a lot of faltering. That is, the performance of this orangish plot or reddish plot here is with the DA algorithm, which is DAN in this case, done with these two corrections, one which is this resampling correction and the other is this reweighting correction. And those two corrections sort of avoid a lot of faltering that we otherwise see. And individually, those corrections also help. And we see that this is not only for that algorithm, but we have many more plots in the paper. And here I've included a bunch, like a subset of 3, where we see that these corrections fix like these methods from like different categories, either domain alignment or self-training or test time adaptation methods and such. If there's any question here, I'd maybe pause. But this is exactly, I think, the thing that we're trying to highlight. Like in some sense, maybe next slide I'll show a plot of So in this slide, we show that the methods that were specifically proposed to handle these relaxed label shift problems actually don't end up handling these, but instead these simple corrections, which are reweighting and resampling, do the job much better for us. And Sentry is close to like I've tabulated these plots in a way so that methods that have similar objectives are together. So Sentry is very close to fixed match and has some it has some objectives that tries to correct for label proportion shift, but it actually ends up not doing it very well. Yes.
So, the resampling actually is trying to change the classifier itself.
Yes.
And the reweighting is just a post-hoc.
Post-hoc correction. Yes. Both are trying to change. Like reweighting is changing all layers. Resampling is just changing the linear layer. Is something that maybe we can say. Right. Because like.
But reweighting in some sense is treats the classifier classifier as a black box.
Yes.
And resampling is really opening a black box and trying to.
Yes. In the sense that it's using it's using the classifier still as a black box because it's just using its pseudo labels in some sense. Okay. One more interesting observation that we have is what happens if we employ different black box classifiers for these label shift estimation methods. So one can think that we can use source classifiers versus these domain adapted classifiers to get an estimate of target label marginal. So recall that these label shift estimation methods use a black box classifier to provide us with an estimate of target label marginal. In this plot, we see that these domain adaptation methods, one, improve our estimation, and two, those improvements in sort of estimation transfer to significant improvements in accuracy. That is when, let's say we are using a source only classifier and trying to estimate the label marginal in a situation when there is no label shift, then often what we observe is because there are shifts in P of X given Y, our estimate will actually be bad if we have like a, let's say a source only classifier, and that can actually end up hurting the performance if we reweight with respect to those label, like those importance weights. But at the same time, estimates that we get with, let's say, a classifier that is obtained with fixed match, reweighting with those estimates often doesn't hurt and sort of maintains the performance that we otherwise see.
Question.
Yes.
Yeah, it seems to me as if part of this is the like maybe one of the things that makes this work is the fact that the P of like X given Y or P of Y given X, whatever, doesn't change that much, even though you are basically varying like your proportions, but P of, so even though there's a shift in the kind of like the like you can say the data generation process, it's not that big of a shift. And I think that's what's allowing you to basically apply this, I think the last step of reweighting basically.
Exactly, and that was the motivation of the work, that, okay, if we allow for these natural shifts, which are not that severe, what happens?
Okay, cool. And there's one comment that I wanted to mention, which is like, is there anything, did you observe anything in the kind of like the natural shifts that also tell you something about the regime in which P of Y also shifts? So right now you're assuming this kind of like balanced in the middle, kind of like, balancing uniformly. But if structurally you observe, let's say the shifts are more on one end or another, then you could basically use that as a better prior for your meta.
That's a great question. Yes, that's a great question. And I do have some findings which are not here, that they're in the paper, where it is the case that if we have information about what label prior you should sort of balance towards, and if your source is already very skewed and your target is skewed towards that, then that helps a lot. So yes, an answer to that is yes. Like if we have that prior information about, let's say, the source label marginal being not uniform and target will be close to, let's say, a mean of the source label prior with different Dirichlet parameters, then yes, in some sense, calibrating to the original label prior and not the uniform helps.
Cool.
Okay.
Just a quick question. So then on the left hand of the plot,
yes,
I'm surprised. So both resampling and reweighting are aiming in some sense to correct for label shift.
Yes, but resampling is correcting to balance, like resampling is correcting by balancing the source and target distributions to have like the same label proportions. And now reweighting is taking a classifier.
I get it. My question is, why does it improve on none? Like at that end, when why is resampling at least actually both maybe, but why is it helping at the left end of the plot where there's only a natural P of X given Y shift, there's no P of Y shift, but I'm doing resampling, I'm doing reweighting.
Yes, so if you see, reweighting actually doesn't, okay, so maybe not this plot, but
but in this plot,
so in this plot, so this is estimation error.
Yeah.
And this is, so I don't have fixed match without reweighting here. That's why I want to go to maybe previous slides. And maybe that will become clear. So it doesn't actually help. So if you look at this plot here, it doesn't actually help. Yes. And often in some cases, it may hurt because of.
You're doing something.
Exactly. You're doing something, but you should not. So yes. And okay, one more behavior that we observed with respect to early stopping is in problems where these label proportions shift, early stopping criterion ends up mattering a lot. So here in the left plot, we are showing accuracy difference between an early stop model that we choose with target validation and source validation. So the difference is, so the difference here is the difference between accuracies of early stop model with using target validation as an early stopping criteria and source validation as an early stopping criteria. And note that as the label proportion shift becomes a lot more severe, the difference is actually huge, which basically shows that if we use target early stopping criteria, it may give us a false sense of progress, even when our methods are actually not, like in some sense, when we don't have access to target validation data, we may not be able to sort of select that early stop model. And on the right, we see that that happens for all different methods, but yeah.
So the accuracy difference is what minus what?
So it's accuracy difference between a model that is early stop with target validation. So that is, let's say, minus source valid, yes. Yes, and more recently we have one theoretical result where we're trying to like characterize how these label shift estimation techniques actually would behave when we start introducing these shifts in P of X given Y. And we have this result where we observe that if we have access to, let's say, infinite unlabeled data and infinite labeled data from source and unlabeled data from target, then the bias in your estimates is directly proportional to some form of PV distance between your source P of X given Y and target P of X given Y, and there is a max here. So this PV is basically the max PV across all of your labels. So we do see that as the shift becomes more and more gradual, these methods will sort of degrade gracefully in terms of how well they're estimating the target label margin. And if your classifier F can take into account like the shifts that are happening in your X space, then this bound also shows that even when your shifts in P of X given Y can be huge, if your classifier representations are relatively better in the sense that the shifts in representation space is happening to a lesser degree, then we'll hit with respect to that shift, not the shift in original input space.
Is this when the number of test points and source points are both going to infinity? Like this is an asymptotic
Yes,
state.
yes, asymptotic signal. Yes.
So you do expect zero if there's
No,
shift.
yeah, exactly. So we do get, yes, exactly. And
But
I have one more result where basically we have this term plus a finite sample error, which has a 1 over square root n. So yeah, to conclude, we basically show in our work that relative to benchmark-driven work in domain adaptation literature, RLSbench sort of provides a more comprehensive standardized suite, and more than that, this provides a sensitivity analysis to measure how robust different techniques are with respect to various perturbations, either in P of X given Y or either in label proportions, by taking methods from either literature and sort of trying to use these methods when both of these can shift. And we believe that this is one step closer to the kind of diversity that we may encounter in practice while deploying models. However, we have this word of caution, which is while these results are promising with our meta algorithm and the default, like the existing domain adaptation techniques, given that these problems are sort of underspecified, we should take like benchmark results with grain of salt, and we should always think about how are the shifts that like what are the kinds of shifts that we may have in our data set, and that may also like tell us more about the kind of problems or like the kind of methods that we should leverage. And yeah, there's future work which we are actually currently exploring on how can we sort of characterize the behavior of these different methods when label shift assumption is violated, and also there is some prior work that analyzes fixed match when label proportions don't shift. So we're trying to see now when label proportions do shift, can we highlight like a theoretical failure with these self-training methods? And more work is to be done to try other kinds of methods like self-supervised methods that take unlabeled data from source and target, train some representations, and then fine-tune on source label data. So we have not evaluated those kinds of methods like SimClear or like SWAV, which basically learn the representations first only from unlabeled data. Yeah, if there are any questions, I'll take them. Otherwise, yeah, we have recently open sourced everything. We have open sourced our benchmark. The paper is also out, and yeah, all the resources can be sort of accessed online. But yeah, thanks.